So we're going to talk first about data-driven optimization with contextual information. So how do we utilize contextual information to make the best informed decisions under uncertainty? So the motivation for this is a real case application that we've worked on, which is how to trade wind power and hydrogen under uncertainty. So what's the motivation for this application? So Denmark has some pretty ambitious goals regarding green hydrogen and the development of electrolyzers, with a lot of support for building new electrolyzers, up to 6 gigawatts by 2030 of electrolyzers to reduce CO2 emissions. So you can see here the map of where Denmark is planning to build this new electrolyzer capacity. Why does Denmark have this ambition of producing green hydrogen? Anybody has some ideas of what's the why? What's the point of green hydrogen, especially for Denmark? Yes. So yeah, replace natural gas or fossil fuels in hard to decarbonize industries, for example, shipping, so heavy transport. But this also motivated by the electricity mix in Denmark, right? We have a lot of wind and some hours where we have excess wind. So using then this excess wind and create some value from it to produce hydrogen is one of the motivation. So in this context, we've worked on a project with Siemens Gamesa, funded by EUDP, about how to operate a hybrid power plant. What is the business model for a hybrid power plant? How could they make money by selling electricity and hydrogen? So we looked at this small demonstration site that's in Denmark that has a wind turbine, some electrolyzer, some hydrogen storage, and a small battery. And the question was, how can we trade in day ahead and schedule the hydrogen production, knowing that we have uncertainty on the wind production and the electricity prices? So this was a very real case study, and you can see here the proof, because this here is Jalal and this is me and some of our PhD students visiting these demonstration sites under the rain. So that also tells you this is in Denmark. So the goal was to try to make decisions for this hybrid power plant. So specifically, oh, I didn't know there were animations. Okay. So what does this hybrid power plant actually look like? So as I said, we have some renewable energy sources. So you saw the wind turbine that is producing electricity. With this electricity, what can we do? We can export it to the grid and trade it in the day-ahead market, or we can use it to produce hydrogen. If we produce hydrogen, then we have some pipeline of compressing it, storing it, and then exporting it using some tube trailers. With the hydrogen production, this electrolyzer is a flexible load, technically, so you could also provide ancillary services to the grid by adapting your demands. But for now, in this example, we're not going to talk about this. So we're only interested in optimizing the energy of the wind turbine and the electrolyzer. So the decisions we're trying to make are what is the optimal bidding strategy in the day-ahead electricity market? So that means how much electricity should I sell in the electricity market in the day ahead? We're not considering that we're price makers, we're not strategic in that sense. So we're offering the marginal production cost of our units, and we're not strategic in prices. The only decision is the quantity we should sell. And what is the optimal scheduling of our hydrogen production? So how much electricity should we use to produce hydrogen with our electrolyzer? So we're not talking about intraday trading, ancillary service markets. This will come in future research. If you're interested, you can get in touch with Yannick. He's working on this right now. So these are the decisions we want to make. What information do we have to make these decisions, right? So we need some information to make the best possible decisions. Well, we have some parameters that we know, right? We know the technical specification of our assets, how much hydrogen we can produce, what's the efficiency, the capacity of the wind turbine, etc. We also know the hydrogen prices. Typically, you have long-term contracts for hydrogen, so you know the prices and the demand for the following day for your hydrogen production. So this is known. That's good. We also have some uncertain parameters, so some that we don't fully know. And that's the future realization of our wind power production and the day-ahead electricity prices in the following day. So unfortunately, we do not have this full information. So what other information can we use? Well, we have some contextual, what we will call contextual information. So even though we do not know those uncertain parameters, we might have some covariates or predictors of these uncertain parameters that we're going to try to utilize to make the best decisions possible. So what are those covariates or predictors that we can use when making decisions? So one example could be what were the realization of wind and day-ahead electricity prices in the current hour, right? That could give us some indication of what the electricity prices and wind will be in the future. We might have some weather models that we can use to predict the wind in the future. We might also have some forecast of what the load will be in the next day. We might also have access to some forecasting tools from third parties. So in this case, Siemens Gamesa was buying day-ahead electricity price forecast, so deterministic forecast of the day-ahead prices, and was making in-house also some forecast of wind production. So we have those predictors of our uncertain parameters that we want to utilize. And those might be directly the prediction of those uncertain parameters, but there might also be other predictors that are related, correlated with these uncertain parameters. So here you can use any information, any contextual information that might be relevant for making your decisions, right? So we have this type of information. We also have historical values for our uncertain parameters. So we don't know the wind and day-ahead prices for tomorrow, but we know the wind and electricity prices in the past month, year, because we've observed this. So we can also try to utilize this information. And we also know the historical value that those covariates or features, as we're going to call them in this talk, the historical value that they took. So in the past, we can observe the realization, the historical realization of our uncertain parameter and the historical values of our features. And that will give us an idea of how they're related to each other and help us determine, based on the current values of our features, how to make decisions. So, yeah.
Do you get also the forecast error from your provider? The forecast error from your provider, or?
So the provider does not. Yeah. So you asked if we get the forecast error from the provider. So we get a deterministic forecast for tomorrow. So for tomorrow, we do not know the forecast error. They do not give us the variance or confidence interval, but historically, we can observe the forecast errors because we observe the forecast they provided in the past and the realizations of wind. Right?
You compute the historical error between, okay.
Yes, so we're going to use this historical data to compute the historical error on the predictions. Right? Exactly. So what we're trying to do is to use this contextual information as much as we can have access to make the best possible decisions. So, just a little background. We're going to go a bit more high level before seeing how we actually solved this problem in our case and why. So what is contextual optimization or decision making with contextual information? If you're interested, there's a very interesting paper, a survey on contextual information, on contextual optimization methods that you can go check out. So the idea is to learn how to map these features or this contextual information to optimal decisions, right? So we're trying to find some model to map our contextual information to the best possible decisions. So what kind of models can we use to map this? Typically, there's two steps. First, the training step, where we train this model. That can be decision-making model or prediction model, using the historical data that is available. And then there's a decision stage, where we apply this model to our new contextual information to make decisions for the future, right? So I'm going to present those two different stages or pipelines, the training one and the decision pipeline. But remember, in the training pipeline, we use historical realizations of our certain parameters and our features. And in the decision pipeline, now we don't have the realization of our certain parameter, we only have the realization of our features. That is our contextual information for today that we use as kind of a proxy to predict our uncertain parameter and make the best possible decisions. So traditionally, right, stochastic optimization is of the kind of predict then optimize framework, right? So in the decision pipeline, you get some features, some contextual information. You use some prediction model to predict the values of your uncertain parameter. Then you use this as input to solve your optimization problem, and you get your best possible decision. So this optimization model could be deterministic, it could be a robust optimization problem, chance constraint, any type of optimization problem that depends on the type of prediction you have. So this is the traditional way, and typically, how do you train your prediction model? You observe historically the values of your features, you train a model that gives you some predictions, then you calculate the prediction error based on the realizations, and you use this prediction error, you try to minimize it when you train your prediction model, right? So that could be a regression model, for example, you try to minimize the mean square error of your prediction model. So this is what is usually done, right, in stochastic optimization. You have those two steps that are separate. What could be a potential caveat or limitation of doing this? Well, one that is obvious is that if I'm minimizing the forecast error, does that mean that I'm going to minimize the losses of my decisions? Is that necessarily the same thing? No, right? You could have some asymmetric losses. So overestimating your wind forecast, for example, in some cases, might give you bigger losses than if you underestimating it. That could depend on, for example, the balancing cost in real time. So this model does not take into account the losses incurred after the optimization and after making the decisions. So what some people have tried to do is keeping this predict then optimize framework to improve the training pipeline to take this into account. So keeping these two steps, some papers that are very interesting, if you want to go check them out, have used some smart predict then optimize technique where when training their prediction model, instead of training it on the prediction error, now they're training it on the decision task loss. So they backpropagate how a prediction error will impact your losses after decisions, and they train the prediction model based on that, right? Then they use this trained prediction model as input to their optimization model. So the benefit of that is that now you are taking into account the loss of your optimization model when you're making prediction. So that is typically quite a big improvement compared to the traditional predict then optimize. But there's still some limitations of this that made us go another route. So one limitation is that the forecast you get with this smart predict then optimize approach does not represent the most accurate forecast that you can derive of your uncertain parameter. So that might be a bit counterintuitive for people who are operating a power plant. It might be a bit, it might lack transparency about how you're deriving this forecast. So that could be an issue for people who are actually using this forecast in practice. Another issue is that you still need to solve this optimization model when you're making your decision. This optimization model might be quite complicated, right? You could have many binary variable, non-convexities. So the closer you come to real time, and if you have a complex model, the more difficult it might be to actually optimize this model. And especially if your prediction model gives you many scenarios with very high dimension, you might have a very hard optimization problem to solve. So we tried another approach. Yep.
Seems to me that seems to me to be a very risk-averse decision-making process. And in the U.S., I don't fully understand what happens in Europe. There would be an arbitrage condition where the virtual players could come in and take that risk because you're you're really not offering your expected production. You're basically being very risk-averse.
So it depends then also of your optimization model, I think, right? It depends how you formulate this task loss, right? You could still be...
But minimizing losses is a very risk-averse strategy.
So the task loss here would be compared to your optimal decision. So it could be also maximizing profit.
My
right?
question is, why don't you bid expected costs?
So, okay. So that's a good question, right? Why don't you bid the expected cost? Let's say, right, you bid your expected cost, and that means in real time you'll have some balancing to do, right? If you're 50-50 sure that you're gonna overestimate or underestimate, let's say now you overestimated, right? Then you know that the balancing, and you have some information that tells you that the balancing prices will be very high, right? So you'll need to buy back this energy at a very high price. So you overestimated, you incur a very high penalty. Whether if you overestimated, maybe you have some information that tells you that the system might be in deficit, in excess anyway.
If the real-time price is a penalty price, a true penalty price, meaning it's higher than the actual real-time price, then I don't disagree.
Yeah. So it's because of this asymmetry of losses that overestimating or underestimating doesn't cause the same loss, right, in your task. So you're still trying to maximize, and you might still make some risky decisions because if you're expected that the system will be in excess or in deficit, and then you bid more than your expected value, then you might actually be quite risky. Yeah. So this approach, great, but we still have to solve this optimization model. So what is another approach that kind of combines those two steps, right, of prediction and optimizing in one simpler decision task? So what if we could directly, right, take our features, our contextual information, and map it to the optimal decisions, right, using some decision rule model that we are going to train. So instead of predicting the values and then optimizing based on them, I want to just, directly learn a decision rule that will map my contextual information to the optimal decisions. So in the training stage, what I'm going to do is use the historical realization of my features, train a decision rule model so that the decisions that I take with this decision rule based on the historical realization minimizes the loss of my task or maximizes the profit that I'm making. So I'm going to train this, and then in real time, when I'm making my decision, what happens? I have a trained decision rule. So the only thing I have to do is use this decision rule, apply it to my new contextual information, and do some matrix computation, just multiply my decision rule by my features, and I get my new decision. So in real time, you could apply this very simply if you are an operator, right? This is also fairly intuitive model for operators. So this is a very practical approach, and this is why we went this way. So now we're going to go a bit more in detail about actually how we implement this decision rule framework in the case of this hybrid power plant. But if you're interested more into those frameworks, you can go check these papers and this survey paper that are explaining in more details some advanced methods for these different frameworks. So we're going to dive a bit more into this decision rule framework, and Jalal is going.
Good, thank you, Lesia. I was enjoying following your presentation, so you could follow. It could be also easier for me. Good, fantastic. So I hope you are convinced. I'm convinced that this prediction, no, what's that? Yeah, prediction and optimization all in one box, what Lesia called decision rule framework, is a good idea. Then we don't need first to predict and then use our prediction, either deterministic or stochastic prediction, probabilistic, in our optimization model, right? Let's do together, combine them. That's one good idea. And also then, when you make decisions, as Lesia said, you already decided your policies, and you don't need to solve a computationally hard problem closer to your decision-making time. Remember what case study Lesia mentioned? We have a hybrid power plant, and we want to determine the optimal schedule of this hybrid power plant in the day-ahead market, and also to learn to determine the optimal hydrogen production plan for the following day. Good. So the first step, as Lesia said, is training pipeline, training stage. So we can do it offline. We don't need to do it close to decision-making time, right? So of course, we want to have a problem with less computational burden, but it's not a big also problem here because it's not a problem that we want to solve it close to decision-making time. Okay, so in our case, the optimization problem is profit maximization, but it could be anything else depending what application you have, right? So we would like to train our model. There is an optimization problem. We will see later what this problem is. And the input, the first input we have is historical realizations of uncertain parameters. So in our application is realized day-ahead prices and realized wind power, right, in the historical time. So from now on, whenever you see a notation with hat, it means realizations. So the set YT shows all realizations, historical realizations we have, including the realizations of wind power in the previous days, day-ahead price, and balancing price or real-time price. We have that, right? Good. So what we can do is that based on our realizations, we can solve a deterministic problem in hindsight, saying that if we knew these parameters in past, we could make our best decisions. So it's not something that we can do in real life. It's like a back testing. We say that if we had that information, what would be the best decisions we could make? So decision making in hindsight, we can use this to see, I mean, as a benchmark, how good our model is, right? So we are trying to maximize our profit with some constraints. And what are they? Our decision variables are our day-ahead schedule for every hour T, our hydrogen production schedule for every hour, how much imbalance we are causing. It might be excess or deficit in the day-ahead market, so in megawatt. And then our objective function also, it may depend on the realizations. Remember, this is optimization in hindsight. And then you have some constraints coming from the physics of our assets, the power balance inside the hybrid power plant, how much the minimum hydrogen demand you have, and et cetera, et cetera. We will see this optimization problem a bit more in detail in the coming slides. And then our output of this profit maximization is our schedule, day-ahead schedule for day-ahead market, how much quantity to bid in megawatt, and also our internal decision, how much hydrogen to produce in every hour of the following day. Is it clear? Very good. Okay, now features, the covariates that Lesia mentioned. Let's see what else, what other information we have from historical data. We have historical features. For example, we have our historical forecasts, right? And from now on, whenever you see a symbol with tilde, it means forecast, historical forecasts. So what we have, when we were working with Siemens Gamesa, they provided us two features, their historical day-ahead forecast before day-ahead market, and also their historical wind forecast. Is it clear? They are not realizations, historical forecasts. And then also we have a feature of one to train, when we train our policy, you will see that, to get an intercept. Good. So what we are doing, and this is exactly what Lesia was explaining, now we would like to develop an optimization model to train our decision-making process, and map our optimal decisions to features we have. So here you see that we have three types of features, so they appear here. Still, we have our previous decisions. They had a schedule for power and for hydrogen. Now we have two extra variables, Q, and we are going to call them policy or decision rules. So what we do here is that, so we have the same constraints as before, the same objective function. We have two extra constraints. And we are trying to find the optimal policy that maps our features, our contextual information, to our optimal decision. Is it clear? So for example, the first member of this vector is day-ahead prices, the forecast, not realizations. And when you're going to make decisions the next day, you have that forecast. You have that values for the coming day when you make decisions. And if we manage to find the optimal values for Q based on our historical data, then the next day You still have features, the updated features, your updated forecast for the next day. If you learn cues, then when you make a decision, you don't need to calculate, you don't need to solve any optimization problem. For example, you're going to say, okay, for this specific feature, my Q is 0.5. So 0.5 times my forecast that will come, that gives me my optimal schedule. Is it clear? Yep. Now we're going to share the mic.
Thank you. I'm just wondering why we are not considering the balancing prices in our historical features.
Good question. What do you think? So features should be something that it's easy to access, and when we would like to forecast, when we like to make decisions, we have that. So yeah, if you have a model that can forecast balancing price accurately, please do that. But in our experience, it's not that easy. And I'm not sure that companies, it's easy to forecast real-time prices. But if you have that, yes, you can add, that's for sure.
The companies presumably update their forecasting methodology all the time to more and more accurate. And if you train on previous forecasts, does that introduce a significant risk of downstream?
That's a very nice question. Do you have an answer? Oh, that's not you. Yeah, of course, that's true. So as long as you use the same methodology, you can that. But always you can retrain your model. You don't need to train once and live with that. No, every day you can retrain, right? So whenever you see that, you're changing your methodology for prediction. Or if you have non-stationarities, still you're using the same methodology for forecast, but there is none, retrain. And actually later you will see that we propose retraining it every day, okay? So it's flexible in that way.
Thanks. And for example, if I have an optimization problem, in my case, the optimization of reactive power, can I use, I don't know, not exactly historical features, but results like power flow, well, the results of the power flows, like the voltages and everything to train my optimization model?
Yeah, of course. For selecting features, I'll talk about that later. You need to make sure about two things. First, they are providing valuable information. So Lesia called them covariates. It means that there is a correlation between those information and what our optimal decisions will be. So that's one thing. So you have to make sure that you are selecting information which is meaningful for your task. One. Second, it should be something that you have its historical values. One. Second, in the decision-making time, you have the values for that features, right? So if, for example, you have forecasted, I don't know, voltage, and I'm not sure that thing exists, yes, you can do that, right? Armin? Wow, that's interesting. I'm talking and also running. Yeah.
Yes. My question is that you are here imposing a very strong equality constraint, and how you make sure that this problem will be feasible.
Very good question. In the training, it's only feasible for the training data, not necessarily for testing. And you will see later that we have also in feasibility restoration stage. You have to have that. And then it depends on your application, how easy is to restore your feasibility. And are you adding a lot of suboptimality or not? I'm going to talk about that. Good. So you're asking a lot of good questions that I will explain in the coming slides. So Q are our policies. So now the outcome of our model is policies. And here we define two policies, one for our day-ahead decision in the day-ahead market, and the other one for our hydrogen production. Good. And what's going to happen? So now we learn from our historical data how we can optimally map our features to our optimal decisions. And then next time that we should make a decision, we have to submit our bids to day-ahead market, to Nord Pool, for example. Then we have updated features. So now we are in the testing phase. So it's tau. So we have our updated forecast for day-ahead price, for wind, and still we have our intercept one. So you already have Qs. You have the new updated features. Now, no optimization problem to be solved. A simple calculations, and you have your optimal day-ahead decisions and optimal hydrogen schedule, and you can submit this to day-ahead market. Is it necessarily feasible? No. We are going to talk about that. Is it clear? Good. Yeah. Good. So we have optimal decisions to submit to market while hydrogen production is our internal decision. Good. So this is what you asked. We don't need to train only once. You can retrain your model every time you want, if methodologies change or you observe any non-stationarities. Good. So that's the first training. So the day after, now you can now you are 1 day ahead. For example, you can train your model based on the last 20 days, data of the last 20 days. How would be what is the optimal length of the historical data? For example, the last 20 days or the last 15 days, it's a hyperparameter. It's like any other machine learning task that you have to decide. And you can use cross-validations or other to tune your hyperparameters. So do you have a question?
I guess you can also give more weight to newer data when you're training online or retraining, right?
Indeed, fully agreed. Good. So what should be our features? This feature is X, vector X. So any valuable information, first we have to know that they provide meaningful information. There's some correlation, which will have access, which we have access to their historical values, and we will know feature values before making our bidding decisions, right? So in this case, we have wind forecast and day-ahead price forecast as our features, but you can think of more features. For example, you can think of buying forecasts from different vendors, or maybe you have your in-house forecast. So each of the forecasts you have at different points of time can be a valuable feature for you. For example, imagine that you have two forecasts getting at 7 a.m. and 11 a.m. both before noon that you submit your bid to the day-ahead market. It could be, if you have probabilistic forecast that you are buying, that probabilistic forecast can provide you different features, for example, mean, quantiles, or different percentile values, etc. You can have aggregate wind forecasts. All the TSOs in Europe, now they are publishing the aggregate forecast for the next day. You can use that as good features, potentially good features. They had price realizations in the previous days. So for example, you know that what the day-ahead price realizations are in the previous day. It might be a good feature for you. Also, I saw that these days people, they are trying to get contextual information from LLMs based on news, whatever, trying to also explain events or whatever happening in numbers and then insert it to their decision-making problem. Well, it might be interesting. I don't know how helpful it will be, but it's good to see. Okay, now you see that we have policies, and I call them static because it doesn't matter what time of the day is, it's fixed values. For example, if you realize that the optimal Q is 0.5, you keep it for all hours of the following day. Clear? But then it's easy to determine, to optimize queues. Do you have any other proposals while keeping these equations linear? Can we have more queues? Can we relax it? For example, you can have dynamic or hourly policies. So you can learn one policy per hour. So you have one policy for every 8 a.m. hours. You train it based on, and then you have a queue for the next day, 8 a.m. Even you can do more. But remember, to do this, you need more data, and you have to make sure that you are not overfitting your model, which is a classic problem for any machine learning task, right? Can we provide even more flexibility here? So I have to make sure that I'm not too far. So another good idea that actually it was originally Lesia's idea is that even we can have another flexibility, O, for price domain. So for example, you can say that depending what our price forecast is, let's say that for day ahead price between 0 and 100 or 100 euro per megawatt hour, I determine one policy, and for the rest from 100 to price cap, I'm defining another policy. You can do that. Yep.
Does that make it mixed integer?
No, not necessarily, no. Though our problem is mixed integer because of the assets, it could be, but not necessarily here. Good. So remember, this is the overall framework. So here, based on the training and historical data, we learn what our optimal policies are, either static or dynamic or with price domain or whatever. And then when we have the updated values for our features, we make decisions. And there is no need for any optimization to solve there. Good. So a question to you. Do we necessarily need a balancing price forecast as a feature here? Actually, you asked Ali already. But, OK, if you have a good forecast for balancing price, you can use that. But do we necessarily need that? No. I mean, you have balancing price realizations, but you don't need necessarily to have it as a feature. So it gives you a freedom. If you don't have it, you can use that. But if you use generic other methods based on either deterministic or stochastic decision making, you need to put some values for your imbalanced price forecast. So that's one advantage. Good. Can we include day ahead price realizations from the following day as a feature? What do you think? Remember, feature means that we have the historical values, and when we make decisions, we have that values. Now, I'm not talking about day ahead price forecast. I'm talking about day ahead price realization. Can we include it as a feature? Originally not, so the answer should be no. But, again, it's a very good idea from Lesia. Yes, let's do that. And then our decision, P day ahead, will be a function of day ahead price. So you are going to have a curve rather than a single value. So here you have day ahead price. Here you have quantity that you are bidding. So now instead of a single value, now you can have a curve, a linear curve. And then you can linearize that. And then you can submit a curve to the day ahead market. So this brings you even extra flexibility. Am I clear? So now, just to make sure that I'm clear, so remember we said P day ahead, which is our decision, in every hour is based on our policies times our features. And if in our features we have day ahead price as one of the features, indeed, we don't know their true values, the realizations, when we make decisions. So what will happen is that our decision will be a function of the day-ahead price. Right? Now, instead of a given value, we have a curve something like this. Here is the day-ahead price, and here is the quantity, P day ahead. And then you can linearize that, and then you can submit a price quantity curve to the day-ahead market.
As we're probably using some deep learning techniques or something like that, how do we ensure that this is increasing? Because technically you could have some issues there.
That's very good. That's very good. So I didn't mention that, but you need to add extra constraints now to make sure that your curve is not decreasing. So actually, if you read in the paper, we add that in the training phase. In the testing phase, you don't know if you have it or not. So you have to check feasibility, and if you see that it's not happening, you have to make it feasible. But you need to add some constraints to preserve that property, that your curve is not decreasing. Very good point. Very good. Full picture. So based on some realizations, some features, you train your model. That's the first step Lesia mentioned. You have some policies. Now based on the updated features, and now you see that we have also, you see that the realizations of day-ahead price now is part of the features, while we don't have it when we in the testing phase. Now we have a bidding curve, which is a function of day-ahead price, as I mentioned. And then the problem is that it's not necessarily feasible. For example, the curve might be non-decreasing. Or, for example, our schedule for electrolyzer might be beyond its capacity. So we need some heuristics or some easy ways to restore feasibility, and hopefully it will be not very costly to restore feasibility. So we have adjusted curves, and then we can submit that, right? And then we can calculate, after seeing the true realizations, we can calculate our true profit. Okay? Good. So, we have 20 minutes left, so we can now see more about training optimizations. So that's the paper that Emil, our former master student, who is now a CTO in a company, growing fast, he published based on his master thesis and presented at PSCC in 2024. This is the training model. And let's walk into that together. So you are trying to maximize your profit, and that's now your day-ahead quantity times the day-ahead price. And that day-ahead price is realized day-ahead price. We are solving this problem based on historical data. It's in the training phase. And then you have to make sure that this is exactly what it's the bound on power purchase and power sale. So if this value is positive, it means that you are selling power, and if it's negative, it means that you are buying power from the grid. Then the second term is about your profit from selling hydrogen. So rho here is just it shows the efficiency of the electrolyzer, and this is in kilogram, how much hydrogen you are producing in every hour T, and that's the hydrogen price. And we assume the hydrogen price is fixed no matter what time we are producing that. And then we have constraints for electrolyzer capacity, how much hydrogen we can produce, and our minimum daily hydrogen demand. For example, by the end of the day, we have to produce at least X kilogram of hydrogen. It comes from our purchase agreements with hydrogen off-taker. Then here, it's our imbalance prices. And here we first, in this work, we go with two price scheme. It means that any imbalance you cause, it comes with a penalty. So it means that if you have deficit, it comes here. So you have to buy in the imbalanced market. And if you have excess, you can sell it, but you will sell it at a price lower than day-ahead market. Right? So always going to real-time market is costly for you. So above our constraints, so this tree is the internal power balance in the hybrid power plant, right? And at the end of the day, this is a news vendor problem. Are you familiar with that? News vendor problem, do you know what it is? So in the news vendor problem, a person who buys papers early morning, he or she should decide how many papers to buy to earn the highest profit, but there is uncertainty what the true demand will be. If the person buys too many papers, at the end of the day, he or she will not manage to sell all of them, so there will be a cost. And if the person buys less papers than what the true demand is, then there will be opportunity cost. He or she could sell more, right? So at the end of the day, the person should decide how many papers to buy without knowing what the true demand is. And here is exactly the same. So your ideal is that you don't cause any imbalance, but you don't know what your true production, wind production will be. So it's kind of news vendor problem, meaning that whatever comes as deficit or excess, it's costly. Good. So to go a bit fast, so we trained our model with different policies. If we have a static policy, one policy for all hours, or one policy per hour, or one policy per price domain, and if I remember correctly, we had only 2 price domains from 0 to our hydrogen price, equivalent in megawatt, in day-ahead, in power, and from hydrogen price to infinity, the price cap. And then we have the last one when we have both flexibility in time and in price domain. And this is our profit, our ex-post profit. And here we see that, okay, when we provide the highest flexibility to our policies, we can earn the most. And then here you can see that, okay, you submit your bid to the day-ahead market, but hydrogen production is your internal decision. You are not going to send it anywhere. So after day-ahead market and after seeing the realizations, still you can tune your electrolyzer, assuming that electrolyzer is fast to change the set point. So you can do some adjustments real time with your electrolyzer, assuming that you know the true balancing price. So with that assumptions, we see that the hindsight is the maximum profit you could earn. It's your upper band. You cannot do better than that, assuming that you know everything. So that's a good benchmark. So in our case, your profit without any adjustment, without any assumption of knowing the balancing price, is almost the same as the hindsight. And with adjustments, real-time adjustments, you can go even closer to your upper band of the profit. And if you solve deterministic, based on the deterministic forecast Siemens-Gamesa has, your profit is just here. You need a bigger real-time adjustment, again assuming that you know the balancing prices, right? So QTO, our model, works way better than deterministic. I don't have a stochastic counterpart to show you that, okay, if we use stochastic programming or robust, how the profit will look like in comparison to hindsight profit. Is it clear? Good.
Thank you. You told in the setup that there was also a battery. Do you also use it for these adjustments?
No. So we haven't added battery yet, but it makes the problem definitely harder. That's for sure. But we don't. Yes, in the site we had this very small battery, not a large one, but we didn't have it in the model. Good. So now let's go to one price scheme. It's something similar to what we have in the US, right? The real-time price could be higher or lower than day-ahead price. So it means that selling power in real time will not necessarily be a cost for you. You may also earn in the real-time market, or you may lose. And non-Nordics switched to a one-price scheme since December 2021, right? But still, if you cause imbalance, you will be asked what is the reason of imbalance, right? Of course, you can earn in the real-time market, but TSO may ask you that how this imbalance has been caused, right? So it's not really exactly. So to answer also to Dick, in US, in my understanding, real-time market is an opportunity for redispatch, and there is no intraday market. Or maybe it's not a big market.
No controlled intraday market. Yes. People can trade intraday.
Here, but remember in US, both data and real-time markets are being cleared by ISO. It's a market. Here in Europe, they had market by market operator. If you want to redispatch, go intraday market. And it's done by market operator. But the real-time market, or balancing market we call it, it's done by TSO. And we are trying to offset imbalances. So in my opinion, real-time market in Europe, it's not for redispatching. You want redispatch, you go to intraday market. That we don't have it here. Good, so now we have a one-price scheme. You can cause imbalance, but again, knowing that TSO may ask you that, what's the reason of imbalance? Is it systematic, or it's coming from your forecast error, or what? So that's the work that Yannick, are you here? No? Hopefully you will watch it later and you will see that if I'm talking correctly or not. Yeah, Yannick and Fazana. Fazana, are you here? Yes. So Fazana, you can confirm. So we did that. We repeated the work, but assuming that the market, the real-time market is one price. And why is it important? Is it still a news vendor problem? Not anymore. In news vendor problem, any imbalance in any direction cause cost for sure. Here, it's not the case. It's gambling. Good. Now again, we have a profit from selling power or buying power. So if it's negative, we are buying. And we have bounds on power sale here. So it's the upper bound. I'll talk about the lower bound. And again, the first two constraints are enforcing our policies. The second term is our profit from hydrogen sale. We have policy for that. It's electrolyzer bounds. And then we now, instead of having single efficiency for electrolyzer, I don't know if you know or not, electrolyzer has a quite nonlinear efficiency, something like this. So this is the ratio, how much hydrogen you produce by consuming 1 megawatt of power. So it's kilogram per megawatt hour. And this is how much you are consuming, megawatt. Sorry, it's not like this. It's something like this. And here it's about 30% of your nominal capacity. So what in this work Yannick tried to do, we had some linear cuts, and we added here in our optimization problem. And then again, we have a minimum daily hydrogen curve. By the way, I'm talking about here typical alkaline electrolyzer, right? So for high temperature solid oxide electrolyzers, the story might be different. And the last one is the imbalance price. Now, any imbalance you cause, it might be positive or negative. It comes with a single price, the balancing price. You may earn, you may not earn. And we have the power balance, our insight, internal power balance. Good. So here, as you see, the upper bound is, this is my nominal wind, how much I can sell power to the day-ahead market. But I don't have lower bound, meaning that I can buy from the grid. So the question is that, is power purchase from the grid permitted? If yes, and typically yes, then the lower bound will be the minus of my installed wind. Or it could be anything. Or it could be infinity. It depends how much you can buy. Is there any bound or not? If you would like to make sure that in any case your hydrogen will be green, Because when you buy power from the grid, you don't know that what the source of the power is. And then you cannot certify my hydrogen is green. Why is it important? Because if you prove that my hydrogen is green, you can sell it at a higher price, right? And also it could be a part of your purchase agreement. So in that case, the lower bound should be 0. It means that in any case, you cannot buy power from the grid, either in day-ahead market or in real time. Or now we have an EU regulation called RFNBO. I don't remember what that abbreviation stands for. Do you remember, Lesia? Marco, you're here, right?
Non-biological origin.
Oh, tell me again.
Big word to say green hydrogen.
Yes, fantastic. So RFNBO has certain requirements, but one of the requirements is that if the day-ahead price is lower than 20 euro per megawatt hour, why that number, I don't know. If the day-ahead price is lower than that, and if you buy power from the grid, then we can call it's green. Because the assumption is that the most of the power in the system is coming from renewables, and that's why the price is low. And if you have that, then Yannick used some auxiliary binary variables to add that condition. So if the day-ahead price is lower than 20, you can buy, otherwise you can't. Good. This is no longer a news vendor problem. We discussed why. But now the problem is that our bidding in day-ahead market is fully all or nothing. It's binary. Do you know why? So under one price scheme, it's well known that the bidding decision is all or nothing. Either you sell everything in day-ahead market or you sell everything in the real-time market. Or if you are buying, again, it's binary. Any thoughts what that happens under one price scheme? It's easy. So you have forecast, right? So for example, if you say that my day-ahead price forecast is 20 euro per megawatt hour, and my forecast for balancing market is 25, they are forecast, right? Then what you are going to do is that you are going to sell everything in the balancing market. And here, of course, we don't have a but here you are training. And in the training phase, you know the true values. So depending on that day what's happening, you will have all or nothing. But the problem is that for the next day, you don't know what balancing price. Either the market will be long or short. You don't know that. So you are going to gamble. And we don't like gambling. So without any extra things, this kind of, where's my remoter? Here, thank you. So without doing anything else, you will see this kind of policies. Either you are buying or selling fully in the day-ahead market. So we didn't like that, and usually, I think there are some people here from developers. Developers don't like this kind of gambling, betting behavior. So what we tried to do, we added some constraints, how much imbalance internally we can cause. So we added extra constraints, for example, on the mean for the next day, or in the training phase, how much imbalance you can cause, or our extreme imbalance we may cause, or on the mean of the tail, so CVAR constraints, conditional value at risk. So you can control how much imbalance you would like to cause. For example, I heard that if you would like to justify TSOs, it could be, for example, your forecast error threshold. That's the threshold of imbalance you would like to cause. It's something that you can tune. Okay, after adding that, and here it's the results with the CVAR constraint, how much imbalance you would like to cause. You see the results, power bit, and here you see the different distributions depending what hydrogen price is. If hydrogen price is very high, like 6 euro per kilogram, or if it's low. You can read paper to see more details.
What's the y-axis?
Pardon me?
What's the y-axis?
The frequency. It's the frequency. It's the frequency. Yes. It's for 1 year, exactly. So the results, yeah, here I didn't mention that. We have 1 year of training and 1 year of testing. So that's the frequency. Good. Yeah, I think I like to go to conclusions since we have only 2 minutes. So decision-focused learning is a pragmatic methodology. Why we are saying that? If we use that, then a company like Siemens Gamesa or any other developer, they don't need to deal with, for example, stochastic programming. I don't know, generating scenarios or using robust optimization. We trained for them, based on their historical data, what their optimal policy is. And then when they make decisions, they know that, okay, my policy for this feature is 0.5. Okay, I cannot just calculate this times this. Plus, if I have the second feature times the policy. Very easy, very understandable for companies. Rather than asking them, okay, let's start predict something stochastic. Now we are going to solve stochastic programming with 1,000 scenarios. Why 1,000 scenarios? How to put the weights? It's less pragmatic, right? It's okay in academia, but I don't know. I never worked in companies, but I assume it's less pragmatic. But this is practical, and it works okay. So, straightforward for practitioners in industry compared to stochastic optimization. I hope you agree. And ongoing directions. So we are now working how we can improve our model. We like to keep it linear. So if you use neural networks or whatever, still you are doing something similar. Just instead of defining linear policies, you are defining something very non-convex and maybe hard to understand it, right? But we like to keep it linear, but we are trying now to use kernelized regression. So while still using linear optimization for training, we are trying to understand the nonlinear relation between features and our optimal decisions. So hopefully maybe next year, Lesia and we can explain about that. Multi-market bidding, so far we have only day-ahead market, hydrogen selling, and in real time. So now in Europe, intraday market is a very big opportunity. Many companies also, they like to have a good strategy in intraday market. And now in Europe, we have two types of intraday markets, continuous, starting right after day-ahead market, until, depending which country in Denmark, until 1 hour before the real time. And it's very complicated how to make decisions there. And also now in Europe, we have 3 auction-based intraday markets, right, in a European level. So it's very complicated how also make this. So hopefully this decision-focused learning can help us there, also to know what to do in an intraday market. Also, you can think of ancillary service markets. It's also a big thing in Denmark. You can participate. If you are flexible enough, depending how fast you are in responding, you can participate in different ancillary services, MFRR, AFRR, FCR. By the way, in Denmark, I like to promote that. We have something called P90 requirement for ancillary services. So I know some of you are from TSOs, so hopefully you will do the same. It says that, okay, stochastic assets, it's very hard for them to participate in ancillary service markets because to guarantee 100% reliability. So, and again, it says that if your reliability is at least 90%, if you can show me ex post that 90% of the times what you bid ancillary service markets, you had it, then you are allowed to participate in ancillary service markets. So it's kind of a chance constraint problem. I bid knowing that it will be available 90% of the times. And I think that's opening the door for stochastic assets like renewables or stochastic demands. So hopefully TSOs, you will think of that. And full cost balancing, that's the last things also we are trying to work on that these days. So again and again at our TSO says that, okay, one price scheme, we have it. You like to cost imbalance, do that, like US markets. I will not ask you why. But if you cause imbalance and it's not helping the system, for example, market is long and you're long, then you have to pay also for the reserve I bought for you, for kilowatt, for megawatt, for your share. And I think it's also a very cool idea. And maybe other European TSOs also think of that. Good. Lesia, I hope that you are happy and I covered well what you also wanted to be covered. And this is the 2 papers I mentioned. And you can check also the codes are available. It's an open access GitHub that you can use. And that's all. Thank you. I'm already 5 minutes beyond the time, but if you have one question, I can answer. Otherwise, I'm available. Yes, Nick.
Thank you very much. Really interesting methodology, but in my opinion, one big limiting factor is that it's based on the assumption that the hybrid power plant is a price taker. And on your first slide, you showed the sizes of which are in construction, so they will have hundreds of megawatts of capacity. So it's a very hard assumption for assets of such size.
They are not going to belong, all of them, to one person, to one entity. Right? There will be many different developers having that. At the moment, what I see that HPPs, they are really in a small scale. So Marco is working for a consultancy. So maybe some developer will have a very huge hybrid power plants in future. And you can discuss that for any kind of technology, right? Saying that also, I don't know, conventional generators might be price maker. But yeah, I don't think at the moment hybrid power plants in Denmark or in Europe, they are at a stage that they can act strategically, one. Second, bidding strategically in Europe is not allowed. So there is ACER regulation, remit, and you are watched. If you exercise market power, and if it's proven, of course it's very complicated to prove that, but if it's proven, you have problem.
Means the strategic bidding, I meant that they will change the merit order, so they may affect the market clearing prices, that it might be lowered compared to what your historical values.
Still we call it price taker. Price taker means that you don't model how your bid may change market price. It may, but you don't model it. It means price taker. Price maker means that I see in my model, I model it, how systematically I can change price, market price, in my favor by my optimal bidding, right? So here is still price taker, but that's good argument that we have to see how the market prices will be changed based on our price taking bidding. And by the way, I'm not making a planning decisions. I'm training every day, so I'll capture that kind of, right? It's not a planning problem, but that's a good point. Thank you.